Hi, welcome to the channel. My name is Wallace. In today's video, we are looking at engineering science and 4, and our topic is statics. Under statics, we are required to know how to calculate the reactions of a beam on two supports. We should be able to draw a shear force diagram. We should be able to calculate the bending moments at any point along the beam, and we should be able to draw a bending moment diagram. In this video, we'll be using this diagram. It's a beam on supports A and D, but in today's video I won't be doing how to calculate the reactions. The reactions are already calculated for, like you can see, but we did a video of this beam on how to calculate the reactions and how to draw the shear force diagram, and the shear force diagram came out like this. We got our reactions, we got 20,2, we got 32,8, and our beam is in equilibrium. Our shear force diagram also was balanced. So in this video, I'm trying to keep it as short as possible. Please watch the video that we did earlier. Our reactions came out correct and our shear force diagram was correct as well. Now, in order for us to calculate our bending moments, we'll be calculating bending moments at B, bending moments at C, bending moments at D. We won't be calculating bending moments at A and bending moments at E. At bending moments at the end of the beam is always 0. Bending moments at A will also be 0. So there is no need for us to calculate bending moments at A or bending moments at E. It will always be 0 because the beam is in equilibrium. So we'll be calculating only for bending moments at B, bending moments at C, and bending moments at D. Now, when you look at our shear force diagram, we have our 20,2 at that point. The reaction A pushes upwards, it goes up from 0, it goes positive upwards. Then the uniformly distributed load drops until it reaches negative 3,8, somewhere there. Then we have minus 13,8 and so on. Now, there is this point where the uniformly distributed load drops and it cuts through our equilibrium line or our 0 line. That point, which we can call point X or point F or whatever that you may choose to call it. At that point, somewhere from A up until B, somewhere in between this length and somewhere along this 6 meters, there is that point where the uniformly distributed load cuts through the 0 line. At that point, there are two things that are happening. Number one is that at this point, that is where we have our maximum bending moments. And also at this point, that is where we have the bending moment diagram changing direction. So change okay. So at this point, there is the maximum bending moments, and also there is the bending moment diagram changing direction. It is the highest point at that point, exactly at that point. Now, the distance from A up until that point is not known. It's somewhere at that point. That is where our point X is. We can measure from our diagram, our shear force diagram. It will give us our distance. However, for us to know the exact distance, apart from just measuring, for us to know the exact distance, we will need to calculate the distance, and we will also need to include the bending moments at that point, because we will need to calculate for the bending moments at that point. So in our calculations, we'll say bending moments at X. I've put bending moments at X because I want to go from the left going to the right. Okay, so we need to know how to calculate bending moments at these points. Bending moments at A is 0, bending moments at E is 0. So we need to calculate 1, 2, 3, 4. Before we need to calculate any bending moments, what we need to remember is that a moment of a force is the force times the distance to that point. So bending moments is just basically us multiplying the force and the distance to that point. So if we say bending moments at B, we are taking all the forces up until B. B becomes our turning point. Alright. In order for us to calculate bending moments, basically we are calculating for moment of a force. Moment of a force is just the force times the distance to that force, or I'll use R since it will be turning. I'll use R as a radius. So the force times the distance to that point, that is our bending moments. The units for moment is Newton meters. In this case, our units are going to be kilonewton meters, because we'll be using kilonewtons times the meters. We'll get kilonewton meters. So we will need to know how much force is acting there, and we'll need to know the distance to that point of each and every force. So if we start with our first calculation, bending moment at X, which I've said is somewhere along that point, we don't know exactly where. We'll first need to know the distance from A up until that point. We know it is not 6 meters because 6 meters is from A up until B. But from A up until X, there is a distance that is unknown. You can measure from your shear force diagram, but it will not give you the exact number. It will not give you the decimals that are required on that point. So what we will say is that from our shear force diagram, this is what we have seen, is that we were at 20,2 and we brought down this 20,2 until it reached our 0. What brought this 20,2 to 0 is that uniformly distributed load of 4 kilonewtons per meter. So 4 kilonewtons per meter, 4 kilonewtons per meter until it reached 0. How many 4 kilonewtons per meter are in the 20,2? So for our distance of X, point X, in order to calculate the distance of point X, what we'll say is that we'll take our 20,2, we'll divide it by our uniformly distributed load, 20,2 divided by 4, that 4, because as we move from 20,2, we are going towards the right. 4 kilonewtons for each meter is bringing it down. So what we are saying is that 20,2 divided by 4, and we get our distance as 5,05 meters. Okay, so the distance from that point up until our point X, this distance is 5,05 meters. From A up until B is 6 meters. So somewhere along this point we have 0,95 meters up until B. Okay, so that 0,95 plus 5,05 will give us 6 meters. So that is how you calculate the distance. This is very important because we cannot resolve the bending moments at X without knowing the distance. So this is very important. Without that, then our calculations are going to be wrong, or our diagram will not get the required marks. Okay, so now we start calculating bending moments at X. When we calculate for the bending moments, what we should keep in mind is that when you are calculating for the bending moments that are going down, we shall use a negative sign, and for the forces that are going upwards, we shall use a positive sign. It is very important because positive and negative will give us the direction of the forces. So all the forces that are going down will bear a negative sign. All the forces that are going up will bear a positive sign. Our forces going upwards are the reactions. Those loads and the uniformly distributed load will get a negative sign. Alright, so for bending moment at X, we are taking the right side. We'll take the 4 kilonewtons times our 0.95. This 4 times 0.95 gives us the entire load at that point, only that distance. We forget about the left side, we concentrate on that right side. We multiply by 0.95 over 2. This is the distance to where we are applying. 4 times 0.95, this gives us the entire force or the entire load that is acting at that point. Then this gives us the distance. Now remember what we said, negative sign for the forces going downwards. Then we go to the next force, plus our negative 10 times the distance from this up to point X. Remember we're looking at bending moments at X. We shall multiply by 0.95, negative 10. Forces going downwards is negative, forces going upwards is positive. We go to the 6, also negative 6 times 2 plus the distance 0, it's 2.095. Okay, so with the distances you keep adding, we have 2 meters plus the 0.95. Remember, we are coming up until that point, our point X. So then we go to our next force. Our next force is a reaction going upwards. We'll add our 32.8. Now this is a force going upwards. It will carry a positive sign. We multiply by 2 plus 2 plus 0.95, which will give us 4.95. Then we go to our next force, which is a reaction. So with our next force, let me write here. With our next force, what we are saying is 4, we are looking at this one, negative 4 times our 2 meters. Then this negative 4 times 2, which gives us 8, will be applied half of this 2, which is 1. So we have a 1 from this point up to there, plus 2, that gives us 3, plus 2, that gives us 5, plus 0.95. So we are multiplying by 5.95, that will be the distance. So we'll add to this force. Alright, then lastly, we are adding a negative 5, this negative 5 on the last part, times our distance from there, 2 plus 2 plus 2 plus 0.95 gives us 6.95. Okay, then we calculate. After we calculate, we'll get 51.005 kilonewtons meters. Okay, this is a lot of work, and like I mentioned also that this will consume a lot of our time. So to be quick and also to save yourself some time, when you are calculating for a certain point, for the bending moment at a point in your beam, just take the shortest side. Whichever side that you take, I took the longest side, which was the right side. There was just too much activity. There was the 10, 6, 5, there's a uniformly distributed load, there's a uniformly distributed load, and we still end up with our 51.005 kilonewton meters. But you can as well just take the left side of the beam and forget about that side. We'll still end up with that. So in our calculations, always take the shortest side, the side with less activity. Okay, let's try and take the left side of this point X. We are just taking this side, we forget about that, don't worry about all that activity. So on this side, what we have, I will start with our 20.2 times the distance to X. X is at that point, which is 5.05. It is a positive 20.2. That is our reaction going upwards. We have a uniformly distributed load. Now this uniformly distributed load is going downwards. It is only acting along this distance, 5.05. That gives us the entire force, uniformly distributed load. Then this, when we get this force, we are applying it at half the distance to X. So we'll take this same distance, we divide by 2, and that is all we have on this side. When we calculate these ones, we'll still end up with that same answer. So it doesn't necessarily mean that you have to do both sides. Just do the easiest side to save yourself some time and also to avoid making mistakes. When you take the right side, there will be too many additions. You have to add the 0.95 plus 2 to get so on and so forth. So chances of you making a mistake will be high, but just take the easiest side, one that you can easily calculate and get your calculations. So with this one, it's 51.005 kilonewtons. Alright, so that is done with point X. We move on to bending moments at B. So now with bending moments, you don't have to worry about the rest of the beam. So if we are looking at point B, we are just looking at this point. We don't focus about the other directions and so on. So bending moments at B, you ask yourself which one will be easy, which one will be having less activity. If we take the left side, we only have to deal with the uniformly distributed and the reaction that we have got. But if you deal with the right side, you have to deal with this 6 newtons, the uniformly distributed load, that and that 5. So it will be a lot of work. So just take the left side. we are not going to deal with X anymore. At this point, we are just dealing with point B. What we have is on the left side. So with B, what we have is 20,2 times now the distance from A up until B. In the first calculation, we are going up until point X, but now we are looking at from A up until B. So the distance should always be to where you're going, to the point where you're taking your bending moment. So we'll be calculating times 6. Okay, and it is a positive 20 since the 20,2 is going upwards. Then we go to our uniformly distributed load plus our uniformly distributed load pushes downwards, so it is a negative 4 times the distance from where the uniformly distributed load ends up to. It is dealing with 6 meters, not our 5,05, so we're dealing with 6 meters. Then we multiply this times half of that 6, which is 3 meters, from that point up until B, which is 3 meters. So you don't need to do the other side. But now someone might be asking, why are we not considering this 10? Because that 10 is also acting at B. Yes, if we consider the distance, we said 10, negative 10 times the distance of this 10 to point B, it will be 0. So the 10 is not having any effect or any moment at point B, because it is acting exactly at B. So we might as well not consider that in our calculations. So this is much easier, unlike taking the other side, and we can get our answer. Our answer was 49,2 kilonewton meters. Alright, so that is how you go about calculating for the bending moments. It is as easy as that. So bending moments at C, it is up to you. You choose the left or the right. Let me take the right side, but whichever direction that you take will always get the same answer because the beam is in equilibrium. So I'm now taking the right side. We are not going to take the 6 newtons because 6 is acting at C already. What we just consider is our 32.8 times 2. It is a positive 32. We add to our negative 4 times 2 times, now the distance from there up to there, it's a 1 plus 2, that's a 3. So we'll be multiplying by 3. How the 3 came about is because 2 times 4 gives us a 8, and that 8 should be applied at half mark of 2. So we have 1 on that side and we have a 2 on that side. That's how come our 3 came about. Then we calculate, we also add our 5, negative 5 times the distance from there up to there, which is a 4, and we get our answer as 21,6 kilonewton meter. Okay, so that is how you go about with calculating for bending moments. It is as easy as that. You don't need to kill yourself by taking the longest side. Just take the shortest side and you'll be good to go. Okay, so lastly, bending moment at D. Also bending moment at D, don't worry about the rest of the beam. We are now just dealing with D. So we just look at this direction, and on this direction all we have to deal with is the uniformly distributed load and the force, that is a concentrated load pushing downwards. So we only deal with the forces at the right. So what we have is that a negative 4 times 2, then we multiply by 1, okay, because our 2 times 4 should be applied at half of this point, which is a 1. Alright, then we add to our negative 5 times 2. Alright, then our answer for the bending moment at point D will be a negative 18 kilonewton meters. Okay, so I hope that gives us the idea on how to deal or calculate for the bending moments at each point. So we have our bending moments. Bending moments at D is negative, it's a negative number 18. Bending moments at C is a positive number 21,6. Bending moments at D is 49,2. Bending moments at X, point X, remember that special point that we calculated for, is 51.005. And if we look at our bending moments, we'll find that bending moments at X is the highest. Remember what we said, at this point X, that's where our maximum bending moments will be, as well as our turning point for our diagram is going to be at point X. Alright, so now we are going to draw the bending moment diagram, and I will take you step by step and just show you how to draw our bending moment diagram. Now we draw our bending moment diagram. As we can see from our shear force diagram, we have that point X, our point of interest, where we said the uniformly distributed load cuts through the zero line. At that point, that's where we have the maximum bending moments, and we also have the turning point for our bending moment diagram. However, if the uniformly distributed load does not cut through the zero line, do not calculate for the for point X. Do not worry about point X if it does not cut through the zero line. You only worry about point X if your uniformly distributed load goes through our zero line, and that is where we get to do some extra work. But however, without our uniformly distributed load cutting through our X, there is no need to calculate for that distance X and so on. All right, so the first thing when we are drawing, we state our scale. Our scale for our we state our scale for the bending moment diagram. We'll say 1 meter is equals to 1 centimeter. You can state it there, and then we'll say for our Newton meters, we'll say 10 kilonewton meter is equals to 1 centimeter. Now this is up to you and how you want your diagram to be. The scale determines the size, it does not change the shape. For if you use a different scale, it just alters the size of your diagram. I think this will be a good number for us. So the first thing, we draw our zero line. Our zero line should represent the length of the beam, which we have as we have the length of the beam 12 meters. If we measure that, we divide this length according to our points, point X, point X, which is 5 point. Okay, so we divide our zero line. This is point X, this is point B, C, D, and E at the end there. Okay, then we go at point X. We take our bending moments at X that we calculated for. We got 51.005 kilonewton meters bending moments at X. We take this value, we divide by our scale by 10. We are going to draw a line 5.1 centimeters to represent this. So with the bending moment diagram, it is easy. Just go at X, draw this line, but a dotted line, not the actual line, a fainted line or a dotted line. 5.1. We mark our point and we'll call this 51.005 kilonewton meters. Okay, that is our point. The distance from that point up to our zero line is what we have as our distance in centimeters according to our scale that we have used. If you use a different scale, the distances are going to be different. Okay, we go to point B. Bending moments at B, we have 49.2. That 49.2, we take it through our scale, divided by 10, it will give us 4.9 centimeters, 92 centimeters. This is what we are drawing. This is the length from B, and it is a positive. If it is a positive value, you'll be going upwards. If it is a negative, you'll be going downwards. So at point B, we'll go upwards by 4.9, vertically upwards. But this is not your line that you're aiming for. It is just a dotted line to give you a value. That is our point there, 49.2 kilonewton meters. Okay, then bending moments at C. Bending moments at C, what we got was 21. It's a positive number. We divide by our scale. We will be drawing 2.16 or 2.2 centimeters going upwards, vertically upwards. We'll give it a value as 21.6. We go to point D. Point D, we got bending moments at D gave us a negative 18. Negative 18, we divide by our scale, we are getting a negative 1.8 centimeters. So this negative 1.8 centimeters, it is a line from D going downwards, and the length of that line should be 1.8. Negative 18 kilonewton meters. All right. Now, from A up until B, what we can see is that it is a uniformly distributed load. Where there is a uniformly distributed load, you draw your line, you connect your points from 0, you connect to that point, you connect to that point, you connect those points that we have up until we reach our 0. Because bending moments at the end of the beam A and at E, it is always 0. So we are connecting from there, we go in there to 51, and we are going to 49.2. Now, where there is a uniformly distributed load, what you would draw is a freehand drawing, a freehand curve, a nice curve, and then you aim for that point as your maximum or your highest point of your curve, and it changes direction at that point. Okay, so just a smooth curve, a freehand curve. At that point, we have now dealt with the uniformly distributed load from A up until B, with our point X being the highest point of our curve. Then from B to C, when we look at our shear force diagram, it's just a horizontal line. These 2 points from 49.2 to 21 to be a straight line. From point C to point D, again to be a straight line, you connect with a straight line, you just use your ruler. However, at the last part from point D up until E, we have a uniformly distributed load, and this will now also be a curve, a freehand curve from that point up until you reach your 0 line. So this is how our bending moment diagram will look like. With all those values, they'll give us all the marks for that. So now let me emphasize this part. If the beam carries a uniformly distributed load, wherever there is a uniformly distributed load, it's a freehand curve. And when it is on the positive side, you have curve, it only curves as a convex on the positive side. So on the positive side, whether it is rising, it will be curving as a convex. And when it is in the negative side, on the negative side, it only curves as a concave. Alright guys, please watch the video in the link below for how to calculate for the reactions and how to do the shear force diagram. That is all for today.